circles are inside each other, right?
Yeah.
What happens with the radical axis? Yeah.
This is why you don't.
Okay. And like knowing, so I mean, if you know where the line is, right, you can just remember it, okay, and it probably is just as effective in your proofs for all the problems, right? But understanding it is kind of interesting. So, and I think the interesting thing about this particular thing is that it's not independent of the other ideas. Yeah, they're kind of related. That's what's interesting. If it was just another thing and you had to figure it out from scratch, right, then it wouldn't be that interesting. Okay, so right, so remember we had like two identical circles, right? Yeah. If you had two identical circles,
yeah.
I kind of do. Yeah. So if you have two identical circles, the radical axis is just the midpoint. The line through the midpoint.
That's kind of obvious.
It's kind of obvious, yeah. So basically, what it's saying is, if you reflect the circle, right? You see that? If you reflect the circle, it has the same radical axis. Yeah. Like. Yeah.
Wait, do you mean midpoint of the two sentences?
Yeah. But if they're identical circles, but
Oh, they're identical. Yeah.
But if one's really big,
not
okay, right? Can you see if you we know the radical axis is in between, right? Yeah.
It can't be within one circle because like.
Yeah, we actually proved this explicitly, I think. But
it can't be positive for one and negative for the other.
Yeah. Okay. And it can't be like over here. Yeah. That's important. Yeah. Okay. So, what if you reflected the smaller circle about the radical axis?
Oh.
Yeah.
Genius.
Oh, because the smaller circle has to be, by definition, has to be.
So this is not in the book. This is not in the book, but I just thought this was cool, right?
Like what?
Reflect the small circle, okay?
Inside, and it'll fit fully inside the bigger circle.
It has to fit fully inside, right?
Okay.
Why?
Because otherwise, if it doesn't fully fit inside, if you reflect it again, it won't be fully outside.
Oh, that's a good argument.
Huh? What do you say?
They're saying if it intersects when you reflect it, reflecting it again should undo it, right?
Yes.
So the point of intersection.
Oh, okay, I get it. Because then it'll contradict itself. Because when you flip it out, it should be the same, but it's not. So you can't because. Should I connect one?
Yeah, but another thing is when you reflect this, right? Yeah, it has to be on the left side. That's obvious, right?
Yeah.
And if it intersects, then the line should be on the point of intersection, shouldn't it?
Yeah.
But it's not, is it?
It's not.
It's not intersecting that circle at all, right? So it can't intersect when you flip it, and it can't go like over here, because the line has to be in between, right? The point is when you reflect it, wherever the circle is, let me have another pen. Wherever the circle is, right? Yeah. It has all three circles have the same radical axis. Yeah. So it has to be. If this was outside and not intersecting, the radical axis would have to be in between them, right? But it's obviously not, right? So this is an interesting idea, right? It doesn't prove anything. Well, it proves that there exists some configuration of circles where the radical axis is on that side, right? So like there exists some configuration where the radical axis is like that, right? Which is not solving the problem, right? Of what is the radical axis for circles that are inside each other. But it's completely like the entire idea is enough to tell you how to solve the problem, right? Then you make a guess that they're always going to be like that, and then you just have to prove it algebraically, right? You just need to show that the x vertical line, the values on the left, yeah? Are we all good?
Yeah. Yeah, I get it. I'll just...
Yeah, so the fact that you know what happens for the other configurations forces this kind of thing to be related, you know? Yeah, and then, in your test, maybe you'll just write, oh yeah, that's the radical axis. It'll never show up directly, right? But
there'll never be directly...
Like you won't be so proud of it that in the test you say the fact, then you just show you a cool proof of it or something, right? Like just because you can. It's not like that. It's sort of connecting ideas. You get in the habit of connecting ideas, right?
Right, but then if you can reflect on that side, you can also reflect on the other side, right?
Mm-hmm. Right.
Not necessarily.
So if you have the reflection on this side,
Yeah.
there also exists another like, wouldn't there be another like identical step on the opposite side of the like big circle, such that when you reflect it, it gets there again. So then there's two parallel radical axes.
So you could have more radical axes, yeah.
But then like if you like,
But here you know that there's only one radical axis, right?
yeah. But then like if you join the other one, you realize that like it's not true because
Join which one?
like so if you join the radical axis on the other side.
Yeah.
If you join the sub, like,
Why is there a radical axis on the other side?
Because you reflect the dots. And you can reflect any.
But then yeah, but then if you
Oh,
have the
okay.
two centers of the circle, like the two centers of the circle, like just I'm pretty sure it's pretty clear that it's not true.
Oh, okay, so you're saying like it's left instead of right.
Like yeah, I'm not like it seems like there should be both, but then one of them doesn't work if you just expect it.
Yeah, right. Yeah, and then there's other ways to think about it, I guess. Like, I mean, if you have a circle and a tangent, we know the radical axis is that tangent line, right? And then maybe you can think of it as sort of like I don't know, this is not really a continuous
Like
thing.
slightly.
Really close, right? And then where should the line be? You know?
Slightly out.
Okay. So, yeah, so that was kind of cool. Yeah, and the radical axis, you know, it has a lot of,
Practical applications.
it's like AIMO test question applications.
Prove that there must be a practical application for this to get your marks.
Yeah, like, do you remember how we showed at some point that, like, the ortho center exists, right? Yeah. It was like, yeah, so the radical axis theorem, I guess, it's like all those things in one, right? Like, where the radical axis is for all the configurations of two circles. When you have three circles, they meet at a point, yeah? Called the radical center. So all that stuff is the radical axis theorem, yeah? Okay. So if you have a triangle and you made a circle with AB as a diameter, yeah? So AB is a diameter. So then the altitude lies on the circle, right? Similarly, if you made with AC as a diameter, yeah? Right? So the altitude, so the radical axis of those two circles, right, is the altitude.
Yeah.
Yeah.
True.
Because it intersects at A and the foot of the perpendicular, right? Yeah?
Foot of the it doesn't look like it. But okay, yeah, I
Stop
get
drawing
it.
the circles.
I get
okay?
it.
Yeah. So it intersects here and there, so that's the radical axis, right?
Yeah.
So if you just switch the two sides with these other two sides, right?
Yeah.
Then the other altitude is another radical axis, yeah? Okay. And then the third side is the other radical axis, right? And the fact that they're concurrent is a consequence of, it's another way of expressing that, right? It's the radical center. So see, where, like, you know, the fact that it's concurrent is like a fact, right? Proving it in two ways maybe it's useless, right?
Concurrent. What does
Immediate at a point.
Oh, okay.
32.
Concurrent. I just haven't heard of that word for a while.
It means like. No.
Yeah, I guess two lines is not that interesting when they intersect, but when three lines intersect at the same point, yeah, that's it.
It's just like three.
Concurrent.
I always confuse it with collinear. I don't know why.
Yeah, because that's so complex.
It's related to collinear, sort of.
Well, not really.
Well, yeah, it's like the intersection. It's like a little bit dual. Like it's an intersection of three lines. It's like
It's
from
like
the point of collinear concurrency, and then like a line going. It's like one line going through 3 points, yeah?
Yeah.
As opposed to however many lines there would normally be going
Three
through.
lines going to one.
Yeah.
How I mean.
Yeah, like I guess if you have like 3 lines, there could be 3 points of intersection, right? And if you had 3 points, there could be 3 lines joining them. Yeah? So there is a bit of a duality.
Nice.
Alright. Okay, I guess while we're here, maybe we can do some more observations while we're here. So, can you see that any...
Wait, so how do you prove that the base is also? Oh, okay. So you prove that the base. Okay, it just doesn't look like it. Right?
Yeah.
So this is 90 degrees. So, and also the base has to be inside both circles.
which base?
Like
Yeah, that's
like
pretty cool.
the middle of CV. So like so inside CV.
Yeah, sort of.
It
Yeah,
has to be
come on,
inside
mate.
because it's 90
So
degrees.
this thing is in the book, yeah? What?
Because it's 90 degrees and it's a diameter. It's connected to a diameter, so it has to be inside the
This
circle.
one?
Yeah.
Yeah, that's the point, right?
It's
So-
90 degrees.
So
and
the point of
connected.
intersection of, like this point goes through that circle.
Oh, yeah, I
and
get
goes
it.
through that circle, right?
And it has to because
Yeah,
it's
and we defined it to go through A. So then that's the radical axis because it goes through the 2 points of
it
intersection.
has to go through there
Yeah.
because
Mm-hmm. Okay, so let's label these points. How do we label these points? D, E, and F. So maybe make this F. Oh, wait, I didn't change any of the labels. Oh, you've already labeled it. Sorry. Yeah. So I guess on this. Yeah. So for example, H is on this circle that goes through A, B, D, F, right? Oh, no, it's not. It's not on the circle. It's inside, right? But the power of H is like, what is it? HA times HD, right? Yeah. And so these are all meant to be equal now. So H.
what HA times HG?
Yeah.
The power of the point.
Yeah,
Power
so
of
this is equal to HE times HB, right? So that's just from the same circle. There's like the same point has the same power with respect to the same circle. Yeah. And then if you look at any other circle, you'll get that this is also equal to HC times HF, right? So basically it has the same power with respect to all these
So
circles.
wait, what theorem are we using here to multiply the two?
Oh yeah. So the whole point of the power of point thing was that when you have a circle and a point, yeah, like the products of the intercepts,
Oh, this
that
is
times
the
that
first
equals
theorem.
that times that. Yeah. So that's like, so we're in this circle with diameter AB, right?
Yeah.
The product of the intercepts is HA times HD
D.
and HE times HB. Oh no. Yeah, HA times HD and HE times HE.
In the
Yeah.
in
So in this circle.
Since H has like equal power.
oh, because they're equal. The
Yeah.
HA times HD equals
Yeah.
to
So
HB.
H just has equal power with that own circle because power is well defined, right? But
What
then
does well defined mean?
it means like
Oh, it can
you
only
get
be
one
like
answer.
defined by one thing.
Yeah. You get one answer no matter where you take the starting point. Like, that's allowed. Okay. So, okay, so you get this as equal, right? And it's kind of interesting that if you took any, I guess it's Sevian or Chevian or whatever, so if you took anything like AX, right? Or AA0. If you took any of this as the diameter, then it would also pass through D and A, right? Yeah. So if you replace like this side by AX, and you replace like this side by like CY or something, right? that make sense? Yeah, and you replace this one by VZ, yeah?
Are they
Oh.
intersecting?
Well, they might not intersect at a point, but they have the same radical axes. Like, we haven't created any new radical axes by introducing these circles. Does that make sense? So what I'm saying is like, if you take x to be any other point, right, and you took ax as the diameter of a circle, right?
Right.
That circle, yeah, that's like all those circles together with those other two circles will still have this AD as the radical axis.
Oh yeah, that makes sense. Because they
Yeah.
all have to start from A, and they all have to have B.
Yeah.
Wait, they don't have to be 90 degrees anymore, though.
But what about like CY?
But
CY.
They don't have to be 90 degrees anymore.
Yeah, so CY will get pass through CF.
Yeah, but like, what is the radical axis? Oh, are you just saying like that's the radical axis from like any point? Okay, yeah.
Yeah, so I guess what I'm saying, yeah, like if you can replace, yeah, like if you add these circles, the conclusion is the same. Yeah. So basically, this orthocenter should lie on the radical axes of any of these circles. So, there's tons of circles with radical axis. So if you had a family of circles with radical axis AD, right? That would include like all the circles with diameter AX as X varies. Yeah? Okay. Yeah, so that makes sense. Yeah, so but it doesn't mean that they always meet at a point like this. Does that make sense? So like the radical axes will all pass through the H, right? But there might not be three different ones. Like some of them might be like parallel or something. Yeah, it might not. How would you say? Like they might not always just be one point. Yeah. So let me just demonstrate this.
So when you drew the line, when you created the lines X and CY,
Oh, actually, yeah.
wait, didn't the original radical axis was based on the 90 degrees of the ortho of the altitude?
Mm-hmm.
So how did you draw the lines A, Y, and C? X and CY when they're not right angles anymore?
They're not right angles, but they'll still have, like, if you're the diameter, they'll still have the altitude as, like, it makes a right angle on the circle.
Oh, okay, sure.
Yeah. Oh, actually, while we're here, there's there's a theorem in the book that we might as well just talk about because it's not too far off. So there was a theorem that said, okay, so is it clear that, so there's this thing where they said, like, the orthocenter and ABC, right, form what's called an orthocentric quadrangle or something. So basically what it means is if you have those four letters and you remove, it's like, if you take three of them, the other one's the orthocenter. Oh, you've done this, okay. So like if you have ABCH, right, like A is the orthocenter of BCH, B is the orthocenter of ACH, and C is the orthocenter of ABH. Yeah? Huh? And it's allowed to go outside the triangle and stuff. So like if this is A, B, C, right?
Yeah.
H is somewhere on this.
Here.
H. Yeah, and then so A, so if you see AHB, right?
Okay.
Yeah.
The orthocenter.
So AHB, so the altitude of AHB is this line, yeah? Yeah, goes to H. That's the altitude.
Yeah.
And then it keeps going, yeah?
Yep. Hit C.
Yeah, and the altitude of this from A is this line, right?
Okay, that makes sense.
Yeah?
That
makes sense. So
But
if,
isn't it the like altitude from A is the one that goes to AC?
okay, so let's look at A, H, B, yeah? Yeah, so the altitude from A goes here.
The other one. It goes to BH extend.
So it has to be perpendicular to this, yeah?
Wait, altitude from A.
Oh, sorry, yeah, B, sorry, yeah. So this is the triangle we're doing, yeah? So the altitude has to be perpendicular to BH and pass through A. It goes from A to this line, yeah? Yeah? And then Huh? C is the orthocenter of AHB.
Oh,
Yeah.
okay. So
So one of the altitudes is AC, right? Okay.
does that work for every triangle?
Yeah.
So if H is the orthocenter of ABC, then each point must be the orthocenter of the triangle formed by the other 3 points.
Yeah.
Yes. Say that again.
Huh? So if you delete one letter from these 4 letters,
Yeah.
then the triangle has orthocenter the letter that you deleted.
Works even for obtuse triangles.
Yeah.
Well, this isn't a true. Like
These will be obtuse, yeah.
What? What?
That statement is quite obtuse.
What's the joke here? What does obtuse?
I think obtuse means dumb.
What?
No, it's like
Oh, okay, he didn't know it meant dumb.
rude.
Oh, crude.
Like being obtuse. Like
It's not sharp.
Okay, sure.
Yeah.
Like sharp
Yeah,
is
it just
acute,
means
right?
sharp.
Your wit is not sharp.
oh no, like
It's both.
like the second definition of obtuse.
There's both.
Rude.
Both. Yeah.
Yeah.
Basically not okay.
Yeah.
So things like A, B, C, H.
Okay, and so the theorem is sort of just saying, it says a bit more. It says this forms a orthocentric quadrangle, right? And all the
It's not a
circumcircles,
quadrilateral.
all the circumcircles are of equal radius, or they're isomorphic. Or
Oh, wait.
What does isomorphic mean?
Mean they're congruent.
Yeah, so they don't have the same centers, obviously, but
They're
they have
congruent.
the same radii. Yeah.
Congruent circles. All they have to do is have the same radius.
Okay, I see why this is true. Oh, I've proved it for all the outside.
I bet.
Wait, is it true?
How do we prove this then?
Okay, so one of the ways that they do it in the book, okay, is you extend this to say like U. Let's call it U. Yeah. Is it clear that what's this letter again? D. Okay. Is it clear that du is equal to HD?
du is equal to hd.
How can we be so sure?
You just prove that it's like a kite.
Yeah, okay.
Immediately.
Yes, correct.
Have we all agreed on this?
Because once you join cu and bu,
Yeah, that's why I said prove that's a kite.
You've already done this before? I've just done it now.
Both?
Done it. Or so we're trying to say that this is equal to this.
yes,
How can we be sure?
because
Because
that is equal to that, and these two are equal, right?
How do you prove?
just alpha, beta, off.
Does that go
Oh,
to
okay.
regardless?
Okay, these two are equal. These angles are equal.
I'm going to conceal that one.
Alright, so he's chased some angles. So you're saying this angle is equal to
Wait, so what is this again?
Similar
This
triangles.
angle equals.
It is.
Doesn't mind like this angle just equal to this angle.
Oh,
Yeah,
yeah.
it is.
Cyclic.
Yeah.
And then you have two pairs of
No, it's equal to this
Two
angle.
pairs of equal angle. I'm not sure that's what
That's
the
not.
type is
That's
defined
and
as.
it's.
But then you can just say that.
But do you construct
You can just say that
Yeah,
by
you do.
to make a cyclic
congruent
chord?
triangle.
Well, it's not a type of code. It's a type.
But it's
Yeah,
Oh,
so
okay.
it's-
If you can help me directly
It's
show that
not.
these two are
It's a
congruent.
type.
Yeah.
But then opposite
Oh
sides are
yeah,
equal.
that.
No, they don't.
Yeah, it does.
But it's cyclic.
Oh yeah,
It's
this
not
one.
right.
Yeah, that and the other.
Which one are we talking about?
A, B, U,
A.
C.
And then we just
Oh,
skip
okay,
the
yeah,
other
yeah,
one.
that one. Okay, I thought you were
Other
yeah,
one,
that's
really
good.
dumb.
Wait, so you construct CU
Oh.
and BU, right?
And then your pivot's congruent.
AS.
Yeah.
Oh, it's congruent, right? Is it congruent? Yeah, it's right there.
It is AS.
Oh yeah.
Oh, it's congruent. I get it now.
Yeah, I guess this is an interesting lemma on its own. But yeah, if you do the two angles, then this common side you have the AS. So
ABC is some random triangle.
huh?
ABC.
So can you see that so basically like CUB, right, is congruent to BHC, yeah? But CUB is also the circumcircle of ABC. The circumcircle of CUB it's like the same circle, it's the circumcircle of ABC, right?
One thing,
That makes
yeah,
sense?
this is a
Oh, okay.
misleading diagram. H is
Oh,
not the
right,
center
okay,
of the
so-
Oh,
circle.
what?
The circumcircle of C.
H isn't the center of the circle.
There's
No,
CUB.
yeah.
It's a confusing diagram.
So
Sorry.
that's the
H.
the radius is the same as ACB,
Yeah.
which means that it's also the same as CHB.
Wait, what? Two triangles are congruent?
So
Oh,
CHB
That's good. That's good.
is congruent to CUB.
Yes.
Yeah? They're congruent, yeah? So their circumcircles have the same radius.
So how did you prove
Oh,
that?
the circle around it.
How do you prove that they were
How is
congruent?
it congruent? Is that the one inside and the one outside?
Yeah, I don't think we'll talk about incircles for a while. So.
How do you
I
prove
it's
that
what
those
these
angles that those angle pairs are the
So-
same?
Which angle pairs?
These angle pairs.
So
The
these
boy
two?
dot circles.
Oh, okay, yeah, so this one lies on CU, right?
Yes.
And so does that, yeah?
Oh, okay, I see it now.
And then this,
This
one lies on like
Lies on
I keep getting
D
confused. I
D
always think
D
H.
what?
is it F or D?
Is H the center? Like just the center circle.
So like DFAB is
Okay,
a cyclic
so it's
quad,
not
right?
necessarily the center.
Oh,
90-90.
DFAB.
Yeah.
Yeah,
So
that.
then this is equal to that, yeah?
Mm.
So that was equal to that and this is equal to that. So they're equal to each other.
Oh, okay. So DFAB is a cyclic quad because of those angles.
Wait, DFAB is a cyclic quad.
Because of the 9 degrees, yeah?
Huh? You're cutting. Oh, you 90 degrees, 90 degrees. But what about the small angle?
So as long as these two angles are equal,
Oh,
that's a cyclic quad.
So, oh, okay. Because when you connect the line, the H, those triangles are congruent.
Yeah,
Angles
no,
of the same
that's
arc.
AB, yeah. It's on AB. They make 9 degrees. So AB is a diameter, yeah?
Diameter of what?
Diameter.
So if AB is a diameter, then F and D lie on the circle, yeah?
That's not what
Oh,
I
yes.
Okay.
What? Now you're just making. Oh, okay. They're 90 degrees. Okay, that makes a lot.
Okay, and then the same reasoning on the other side shows these
Yeah, a
two
lot
angles.
more sense. Yes, that was quite difficult to prove.
So
And then
CHB
there's
is
angle.
circle
Yeah,
radius
that
is-
makes sense.
CUB, which is the same circumradius as ABC.
Yeah.
Same for the other ones.
Yeah. So they all the three triangles you can get from this have the same circumradius. The radius of the circumcircle.
The circle is a circle outside the shape.
Triangle. Yes, circum. Circle, not in circle.
Okay, so I think that was theorem 2.
There was some confusing stuff like that.
Circumference.
Some theorem in 2.4. Okay.
Some theorem.
Some random thing.
Let me just look that up.
The circle is the one inside, and the X circle is the one outside.
Oh, but that's
Yeah, we had this thing where in the it was like show that the quadrilateral is circumscribed, and then it's like so that it's inscribed, and then it's like i.e. the 4 points lie on a circle.
What?
And then the next part was like, show it's also circumscribed.
Oh my.
It's just like,
it is times the puzzle.
or it's like,
How would you even solve this problem when the wording is incorrect?
it's like, should I figure out what this means, or should I just show it has all properties?